Swayam Prabha. Digital India. Educated India.
In this lecture, let us complete the discussion on Schlieren and Shadowgraph techniques first, and then we will discuss about model design, fabrication and mounting arrangements. In the previous lecture, you may recall that we discussed about the Schlieren technique schematic diagram, the different components, the optics which are involved, and then we discussed about the change in density of the medium as it moves through the test section of the wind tunnel and how it alters the refractive index of the medium. Keeping these things in mind, we proceed with our discussion. You may recall that we also discussed about the fact that the radius of curvature of the light ray which is bending under the influence of a different refractive index which is there locally in the flow field, the radius of curvature is linked with n using a formula 1 by r is equal to gradient of n. Now, if you look at the total angular deflection of the light ray given by epsilon when it is passing through a test section of width L, then epsilon is given by L divided by R, which will be L times gradient of n. We said that the flow is occurring as a planar flow in the x y plane, and the light rays when undeflected are moving along the z direction. Now, when they get deflected under the influence of change in density of the medium, the total angular deflection of a ray when it is resolved into two Cartesian components, the components will turn out to be epsilon x and epsilon y respectively, which give the deflections along x and y respectively. So, they are given by L times del n del x and L times del n del y respectively. Now, we have a very important empirical equation called as the Gladstone-Dale equation, which relates the reflective index n with the density of the medium rho, where k is the Gladstone-Dale constant, which is a constant for a given gas. Of course, rho is the gas density and n is the refractive index of the medium. Incidentally, for air, n is 1.303, for glass it is 1.5. So, this is a very important equation which will now help us to represent the epsilon x, epsilon y in terms of gradient of density. So, if you couple this equation with the ones which we already wrote on top, you get epsilon x equal to Lk times del rho del x, epsilon y is Lk times del rho del y. In terms of the first order derivatives of density, you have now expressed the components of epsilon. You are seeing a typical Schlieren flow visualization of a sharp edged model placed in the test section of a wind tunnel. A very important thing that you should recall is that we showed that for Schlieren imaging, the Schlieren is sensitive to first derivative of the density. Let us next look at shadowgraph. A typical shadowgraph system consists of a light source, a collimating lens and a viewing screen, apart from the test section of the wind tunnel, which is of interest to us. So, if you look at the Schlieren system, you do not have this part comprising of the focusing lens and the knife edge, but you have a screen instead across the wind tunnel, and the screen is usually kept much closer to the wind tunnel test section. When this happens, we project the light rays immediately after they emerge from the wind tunnel onto the screen, like it is shown here in this figure. What we are seeing is that light rays are bending due to the flow having density gradient, and in some places they are coming close to each other, and in some others they are going further apart. So, in the region where they are coming close to each other, we see bright bands. In regions where they are further apart, we see dark bands. And if they are moving practically parallel to each other, we have a kind of average intensity. So, this incident light rays, the parallel rays, are actually produced by the light source and the lens on the other side of the tunnel. This is the test section of the tunnel as usual. This is the region where density gradients exist. If the screen in the optical setup used for Schlieren is placed at a position close to the test section, the effect of ray deflection due to density variations will be visible on the screen directly. So, we are impressing those light rays directly on the screen instead of focusing them and cutting off part of the light using a knife edge like the way we did it in Schlieren. This is basically the difference in setup between shadowgraph and Schlieren, and what you get as a consequence is a shadow effect. On the screen there are bright regions where rays converge and dark regions where the rays diverge, as we discussed already. Therefore, the shadowgraph effect depends not only on the absolute deflection but on the relative deflection of the light rays, that is on the rate at which they converge or diverge on coming out of the test section. When there is a gradient in the density gradient itself, there will be a tendency for light rays to converge or diverge collectively. The variations in the illumination of the shadowgraph picture on the screen are proportional to the second derivative of the density, because you are talking about, say, del x of del rho del x or del y of del rho del y, instead of just del rho del x or del rho del y, which we saw in Schlieren system. So, when the flow is two-dimensional planar in the xy plane, the change in intensity from point to point can be shown to be equal to k times Laplacian of density. K is a constant, not to be confused with the Gladstone Dale constant though. And you finally can show that this is the representation, which means that shadowgraph is sensitive to second derivative of density instead of first derivative, which is true for Schlieren. This is a typical shadowgraph image of a supersonic flow past a bullet like body. So, with this we completed our discussion on shadowgraph and Schlieren techniques. Now, we will spend some time on discussing about model design and fabrication, how we undertake it for wind tunnel testing. We are seeing a few pictures of typical low speed wind tunnel models where you see finite wing sections made of wood, an airfoil section made of wood which is side mounted. The finite wing section is what is called a sting mounted. We will look at these mounting arrangements in a little more detail slightly later in the lecture. And we have again a sting, a rod like structure at the trailing edge of a finite wing. Here the wing is made out of aluminium, while here it is wood, and there are also some CAD images of models which are shown on the right. Now, when we look at model design and fabrication, we have to first keep in mind what is the purpose of the model. Is it going to be used for flow visualization, or it has to be used for pressure measurement or force measurement? Does it need to be instrumented? there are many decisions which have to be taken. The design and fabrication decisions are also linked with the purpose of the model. You have to choose the material accordingly, the machining processes which have to be used, the dimensions and tolerances which apply, the surface finish that you should get, the layout for accommodating pressure ports or for attaching wind tunnel balance, the model mounting arrangement and positioning system, everything is interlinked. For example, when it comes to material choice, when we do low speed wind tunnel testing, we sometimes use wood or fibers or aluminium, light metals. There are plenty of choices, but usually for supersonic wind tunnel testing, we will always go for metallic models. Also, the stiffness of the model matters a lot because the loads on the model will be significant. If you are doing some experiments on, say, flow transition and turbulence, then you need to have extremely high surface finish if you are looking at a smooth surface on which you have to perform the experiments. So such things matter. The dimension of a model has a lot to do with what is called as blockage of test section. We are not allowed to block about maximum 5%, at the most 10% of the cross-sectional area of the test section. So if you have a square cross-section through which the flow is either moving into the plane or out of the plane, then only 5 to 10% at max of that region can be blocked with the model that you have inserted in the test section. Therefore, dimensions are extremely important. So are the tolerances, because you have to assemble many components and so on. Performance metrics include how easily you can handle the model, how easily can you assemble or disassemble, or you can do maintenance within a short time. The preparation time should be short. Also, the stiffness of the model mounting, attachment and positioning system assembly for the wind tunnel testing has to be checked well in advance, and you have to make sure that they withstand the starting loads of a supersonic wind tunnel. Therefore, a lot of thought, multiple issues and considerations go into model design and fabrication. On the right hand side, in the CAD models, for example, you see greenish and reddish patches, which are essentially components of a finite wing model. Those components are designed in a manner so that we have ease of installing pressure ports, locating them, cleaning them from time to time, etc. We are showing a few examples here to give you an idea about what we are talking about. So here you can see that this is a slender body model, a body which has a large length compared to its diameter. So the length to diameter ratio is a large number, and some kind of tough flow visualization is being carried out by mounting it with a suitable attachment plate, and you can fasten the model to that attachment plate and also control the angle at which you pitch the model, because you have markings on this attachment plate at which you can fix the model. Therefore, there are different ways of mounting a model, attaching a model, setting its orientation, positioning it, etc. When you fabricate the model, before you even fabricate, you have to develop the detailed drawings with the appropriate dimensions and tolerances with every detail, and then you try to fabricate it, and then you try to assemble the parts together, for which detailed diagrams of the slender body is provided. There are some ring-like structures which are put in between, which are called as pressure rings, which contain pressure ports. Drawings of those are provided. The nose region, which has an ogive-like shape, is provided with all the radius of curvature in relevant portions of the model mentioned. And once you do a testing of the model using the pressure ring in place, for example, you will be able to work out how the circumferential pressure varies along the length of the model at different locations of the model length. So ultimately, you have the experiments plan in mind, which you have to execute appropriately by designing an appropriate model and its attachment and its positioning system. Let's have a look at a few more examples here. Here we are talking about a supersonic wind tunnel test section. You can see a side plate mounted here in the test section, and one of the sides of the wind tunnel has been removed. The metallic side plate has been removed so that we have visual access to the test section. You can figure out that these are the two pairs of liners which give you the CD nozzle contour. We are testing sharp fins by mounting them on surface plates like this, and these surface plates are fastened to the sides of the wind tunnel, and this surface on which the fins are mounted is flush with the inner walls of the tunnel, so that the flow smoothly moves past it. Detailed drawings, material specifications, everything is provided. Not only that, because you are testing the fins as a pair, you also want to make pressure measurements in the region in between. So detailed layout of the pressure ports have to be prepared, and then accordingly the model gets fabricated. You can see all the pressure ports available there. Once you have them in place, you connect them with appropriate pressure transducers or pressure measurement systems, which are shown here briefly. You are also able to see some oil flow patterns which have been carried out with it. So these are the fabricated fins, the fin assembly. You are seeing typical models which are used in aerodynamics laboratory. You see delta wing models made out of aluminum. You have airfoil models with the mounting arrangement from the side walls of the wind tunnel made out of fiber. You have a finite wing model with a side mounting. You have pressure tubings which are connected with the pressure ports which are created on the model surface. Several other models and measurement instrumentation which are visible, and that gives you an idea that how models look, how models need to be designed, and also you have to put in a lot of thought in deciding how to mount them appropriately in the test section of the wind tunnel. Here you further see a few more models where you can see a relay pitot tube, for example, which is mounted on a side plate. You can see pressure tubings coming out of a side plate which is already mounted on the test section of the wind tunnel. The tubings are coming to pressure measurement systems, transducers, pressure sensors, which we will discuss later on. Here are the side plates with the vortex generators in place, which we discussed earlier when we were discussing about flow visualization experiments. You have further views of the models that we were discussing about. You also have to design accessories at times for your models. So for example, here you have a system by which you can calibrate your pressure sensors, which are important devices for performing the experiments. So you have to design certain accessories like this for performing your experiments. Now a little bit on how to mount the models in the wind tunnel test section. For example, here you see a delta wing which is mounted by a rod-like structure coming from behind. In the rear part of the model, it has been mounted. So this system is called as a sting. So we have sting mounted models here. So the support of the model is through its base or rear region. This is another view of the delta wing from a region close to the fan of the wind tunnel. Another interesting thing which you have learnt earlier can be seen over here, that the test section is square, while after the test section again the wind tunnel is becoming circular in the diffuser. So you might recall that we had discussed about the transition of these geometries along the length of the tunnel, which you are able to view in this picture. Here is an intake model, which is again sting mounted. So there are two rods which are holding the model from behind, and then there is a side rod which is going to help it mount it with the side plate of the supersonic wind tunnel test section. This is an aircraft model which is mounted on sting. So we have seen several examples of sting mounted models here. There are few more examples here. You have an aircraft model which is mounted on two separate supports, and the supports are located on the bottom portions of the two wings. This kind of a support is called as a strut mounted support. So the two wings of the aircraft are used for supporting the aircraft model. This is called as a strut mounted arrangement for mounting the model. Again, here this is another interesting case where you are not able to see the entire aircraft. The entire aircraft would have a portion on the other side continued, but you just use half of the model, which we call as a semi-span model, and that semi-span model is mounted on the wall of the wind tunnel, basically the bottom wall, and you can make out that there is a kind of a rotating table arrangement on which it is mounted, which means if you rotate this table and fix it at different angles, then you are actually going to change the angle of inclination of the aircraft by changing the alpha, basically. So the flow will come in from this direction, and at that time the aircraft model, the semi-span model, will be facing the flow at different angles. So we had a brief look at different types of mounting arrangements. So in this lecture, what all did we cover? We completed our discussion on Schlieren and Shadowgraph techniques, and subsequently we discussed about different considerations involved in wind tunnel model design and fabrication, and this included models both for low speed and high speed wind tunnel testing. And finally, we also looked at a few model mounting arrangements. Thank you.